Dear students, in this class we are going to study the motion of an object in a non-inertial frame. Note that it is a non-inertial frame. So what is a non-inertial frame? A frame which is not stationary and not moving with a constant velocity. Okay, so a frame of reference motion along a straight line with uniform acceleration is called uniformly accelerated rectilinear motion. That is what the book says. So a non-inertial frame is a frame which is accelerated. That's all, simple. A circular motion is an example of non-inertial frame. You might remember from our previous class, a accelerated frame is not inertial, isn't it? Suppose you are stationary, or if you are traveling with a constant velocity, then you are in a inertial frame where Newton's laws are applicable as it is. You need not have to change anything. Okay. But if it is a circular motion, or if it is an accelerated motion, when the bus, suppose the bus you are sitting in is accelerating, then you feel additional forces on you when bus takes a turn. These are all examples of non-inertial motion, non-inertial frames. So we consider an accelerated motion. So we consider a special case. It need not be uniform acceleration. And see, for example, if a stone is falling, okay, free falling stone, then it has uniform acceleration 9.8 meter per second square, fixed. But it need not be the same. When bus is accelerating, the acceleration is not same throughout. But we consider uniform acceleration. Okay, we consider case of uniform acceleration. Example, freely falling body under gravity is an example, and another example is uniform circular motion. Uniform circular motion means number of revolutions per second. If you fix it, if it is constant, then it is a uniform acceleration motion, or a good example for non-inertial frame. ನೀವು ಜಾತ್ರೆಯಲ್ಲಿ ತಿರುಗುದ್ರಲ್ಲಿ ಕೂರ್ತೀರಿ ನೋಡಿ, ಇನಿಷಿಯಲಿ ಸ್ವಲ್ಪ ಆಚೆ ಈಚೆ ಇರ್ತದೆ, ಒಮ್ಮೆ ಅದು ಒಂದು ಮ್ಯಾಕ್ಸಿಮಮ್ ಸ್ಪೀಡ್ ರೀಚ್ ಆದ ಮೇಲೆ ಇಟ್ ಸ್ಟೇಸ್ ಲೈಕ್ ದ್ಯಾಟ್, ಅದು ಚೇಂಜ್ ಆಗೋದು, ಹೀಗೆ ರೌಂಡ್ ಹೇಗೆ ಕುದುರೆ ಎಲ್ಲ ಇರ್ತದೆ, ಕುದುರೆ ಥರ ಅದರ ಮೇಲೆ ಕೂತು ಒಂದು ಸ್ಪೀಡ್ ರೀಚ್ ಆದ ಕೂಡಲೇ ನೀವು ಹೀಗೆ ಗಾಳಿಯಲ್ಲಿ ಲೈಟಾಗಿ ಹಾರ್ತಾ ಇರ್ತೀರಿ, and it will not change for another 5 minutes, let us say. So that is an example for a uniform circular motion. Okay, ಒಂದು ನೂಲಿಗೆ ಕಲ್ಲಿಗೆ ನೂಲು ಸುತ್ತಿ ನೀವು ಹೀಗೆ ತಿರುಗಿಸ್ತಾ ಇದ್ರೆ ಒಂದು ಫಿಕ್ಸ್ಡ್ ವೆಲಾಸಿಟಿಯಲ್ಲಿ ಅದು ಒಂದೇ ಲೆವೆಲಲ್ಲಿ ತಿರುಗ್ತಾ ಇರಬೇಕು, ಆಗ ಅದನ್ನು ನೀವು ಯೂನಿಫಾರ್ಮ್ ಸರ್ಕ್ಯುಲರ್ ಮೋಷನ್ ಅಂತ ಕರೀಲಿಕ್ಕೆ ಆಗ್ತದೆ. Okay, let us consider the mathematics of it. Okay, so I am going to write the frames of reference. As before, we need 2 frames of reference, y, y dash, z, z dash, x dash, o dash, and we take a point P here, which is at a distance of x dash from o dash and a distance x from o. Just a minute, I just want to add a few pages to this, otherwise it will be annoying in between to do this. I think we have sufficient number of pages. So consider a frame S, frame S dash with the origin at O and coordinates x, y, z and time t, O dash, x dash, y dash, z dash and t. We are still working as classical or Galilean frames. Newton's laws are applicable, so time doesn't change. So that's it about that is about the setting up of the experiment. So this is as before, is moving with a fixed acceleration of a star, only that is the difference. It is moving with a constant acceleration, there it was constant velocity. So we consider a frame S at rest. S dash is another frame moving with uniform acceleration along x dash axis parallel to x axis. So y and z are not changing in this case. So from the figure we know that you can make the constructions. You look at the figure, you can make the constructions as before. X dash is equal to x minus o dash, y dash is equal to y, z dash is equal to z and time invariance, so t dash is equal to t. Sorry. At t is equal to 0, o and o dash coincide. At t is equal to some t not equal to 0, or in other words you can say greater than 0, it will be at o dash is greater than 0. It is moved some distance, so the separated by a distance of o dash, and o dash is given by distance moved in time t. You might remember there is an equation for the distance moved in case of accelerated motion. S is equal to ut plus half a t square, but u is the initial velocity, u is equal to 0 here, therefore S distance traveled with the acceleration is half a t square. So here it is half a star t square. A star is the acceleration here. And or in other words, and that implies x dash is equal to x minus half a star t square. Okay, a star t square. So let us so in the frame S, displacement is equal to x, velocity v is equal to dx by dt, acceleration a is equal to, as before, d square x by dt square. Here S is inertial, Okay, S is inertial. S frame is not moving. Only S dash is moving. Therefore, only frame S dash is non-inertial. S is inertial. Remember that. See here, S is inertial. Therefore, F is equal to m d square x by dt square. I call this equation 1 as they have done in the book. In the frame S dash, life is slightly different here. Displacement is very neat. Okay, you have to just write position, velocity, position or displacement, velocity, acceleration, displacement, velocity, acceleration, and then you just write calculate the force in both the frame of references, and here you will know that it's not the same. So it's the same type of steps in even in our previous classes we have followed, okay, while calculating the Galilean principle of relativity or invariance of time. Everywhere it's the same type of derivation. Okay, so here displacement x is x dash, that is x minus o dash, which we have already written, x minus half a star t square. They have a reason for writing a star. You will know it by the end of the derivation. Okay, a star t square. Therefore, velocity u x dash we call velocity with respect to s dash. Okay, this is the velocity of the particle with respect to s dash is u dash, and that is given by d differentiation of x dash by dt. So d by dt of x minus half a star t square, and that is dx by dt minus a star t. Hope you remember hope you remember how to differentiate. Don't do mistakes here, never. Acceleration we call, let us say, a dash ux dash a dash. So here you can even skip x, for example, if you want. It's not really necessary. You can just take u dash because it's all along the x-axis. Okay, to keep it simple, a dash is equal to d by dt of u dash, or that is d by dt of dx by dt minus a star t. So which is d square x by dt square minus a star into dt by dt, which is 1. So that is d square x by dt square minus a star. So a dash is equal to, just to let us go back, we have here called acceleration. A is equal to d square x by dt square with respect to the frame s. So we just substitute that. So a dash is equal to a minus a star. All right. Force with respect to, of course, with respect to s dash. Okay, force is we call f dash. There it was f, here it is f dash is equal to m into a dash, that is equal to m into a minus a star, or that is m a minus m a star. Now that is equal to f plus f, they use the term I. Okay, so force in S dash is equal to force in S plus an additional force Fi. So that implies force in S dash is not equal to force in S. Therefore, S dash is non-inertial. Is a non-inertial frame. Here, Fi is equal to uh, sorry, F dash is equal to F plus Fi. There is a mistake in the book, just correct it. Is known as the equation of motion. Motion in an accelerated frame of reference. Here, Fi is equal to A star Ma star is known as fictitious force, or its other names are pseudo force, or also known as inertial force. Fictitious force is usually widely used word. Sometimes they use pseudo force. So it depends on acceleration of the frame. Okay, that is very important to remember. It depends on the acceleration of the frame. So where do we see this? It's a frame dependent. That is what this is, frame dependent force. Where do we see this? Say, suppose you might have experienced when the bus takes a turn, you feel pushed to one side. You can just feel it while watching my video. Just try moving your body. You feel it when the bus is taking a turn. Fast, if the bus is fast, then you feel more force because it is taking a turn quickly. Acceleration is high. Okay, so quickly it is changing its direction when the bus is turning. If the bus is going slow, then you don't feel that there was a turn. If it is going very slow, so that is the important term. So it depends on the acceleration of the frame. And there are examples of a ball moving on the floor of a train carriage, an accelerating lift, uh, etc. That we will look into those examples in the next class. So let us stop here for now. All the best.